also imagine that it is a part of let me show a wing. Okay, a wing. Okay, let me show a wing. Right? You must imagine that the cross-sectional shape that I showed for the tutorial question, for the example, is simply the cross-section of any stringers or star flanges or so on. Okay, it's quite long and slender, but for convenience sake, when we draw only the cross-sectional shape of it. So you must always remember this thing is quite long and slender. Okay, so when we need to analyze a wing, for example, okay, when we need to analyze the bending stress of a wing, you can imagine that this part is the wing tip, okay, the other part is near the fuselage, for example. Then there will be lift over the surface, upper surface of the wing. Right? It is a distributed lift force, but eventually you can assume that we can simplify it as a point force, or rather a distributed point force along the main spar or quarter cord. So instead of really distributed over an area, you can have a distributed lift force along the quarter cord. Okay, so if you draw from the cross-sectional direction, okay, if you draw from the cross-sectional direction like this, eventually the lift force will be just one arrow, right? The lift force will be just one arrow, like that, near the quarter cord. Okay, the lift force. Even suppose it's distributed over the area, but we can simplify it. We do the integration, simplify it as a distributed force near the quarter cord. This is not a point force, it's distributed along the quarter cord. Because if we see from 3D, it should be, I don't know how to draw it. It should be distributed. Yeah, it's so bad. Distributed like that. Yeah, the lift force should be distributed along the quarter cord, right? Something like that. Can you imagine?
Yes, yes.
So it's distributed along the quarter cord, but when we draw only the cross section, we see only one arrow. Yeah, so it becomes a point force in the cross-sectional diagram. Good. So now this wing section, of course, we have a lot of other things. Like, yeah, we have for example, we have this thing. Okay, we have stringers here and there, right? We have many of them. Okay, maybe we have a lot of them. Okay, I just simply put some. Okay. Maybe we have like this everywhere, a few stiffeners and so on. And maybe we have also spar web, right? Spar web. Okay. We have spar web also, for example. Yeah. So now your question, your issue is to analyze the bending stress. So now you have the design, you have the dimension, you have the thickness, you have the material, right? You also calculate the centroid. Then you also calculated the moment of inertia, right? So eventually, you have when you have the central and moment inertia of the entire cross section of the wing, right? Means that if you refer back to your equation, yeah, you can use the equation. Yeah, you have the central, you have the moment of inertia of the entire wing. Then you can plug in the values into this equation 2.7 or 2.6. IYY, plug in the value. IXX, plug in the value. IXY, plug in the value. Then moment X, moment Y. You need to get from your analysis, from this analysis, from your aircraft model analysis. What is the value of bending moment? Okay. For example, this particular bending moment is from what direction? Is it MX or MY? So once you identify that, you can plug into the equation. After that, you do the calculation to simplify it. Eventually, you will get also an equation like this, an equation like this. Of course, different values, but eventually the equation will be look like exactly like this one. Okay, you will get sigma equals to AY minus BX or plus BX. So A and B, the values could be different, but the equation exactly is like this. So with this equation, you use a table to apply the equation for all the points. For this question, we have point A, B, C, D. Okay, so you apply the point A, B, C, D, E, F. If you have a wing section like this, you need to identify. Okay, identify. For example, let's use the red dot. Red dot. Okay. Okay, let's say you calculate it for the red dot position. Okay, they calculate it for the red dot position. I don't know. Perhaps maybe the corner you need to calculate something like that. But of course, I expect if let's say the centroid. Where is the centroid? Let's say the centroid is here. Okay, let's say this is the centroid. Let's say this is the centroid. Okay, upper, yeah.
And doctor, that's the center of the whole airfoil, right?
Yes, center of the whole airfoil. Let's say that is the center of the whole airfoil. Then I expect that the stress will be maximum near some point far away from the centroid, right? So you don't need to calculate the stress over here. No. Okay, you don't need to perhaps calculate. I don't know. If I expect that this point don't need to be calculated because from the centroid X, Y displacement from the centroid is quite small, but X is quite large, so I'm not sure. But of course, this kind of point is no need to calculate. Yeah, so you can calculate some point very far away from centroid. Those are the critical points you need to calculate. Yeah, like okay, for example, this point is very far from centroid due to X distance very far and also Y distance very far, right? Compared to the other position, like this current point I'm holding, the Y distance is very big, but X distance is very small. So definitely, if you check back the equation, yeah, if you have an equation like that, it depends on it's a plus sign or negative minus sign, okay? And maybe you don't need to calculate this one, you don't need to calculate this, but you need to calculate this, maybe, okay? Yeah, because you have a program, you can plug in several values and check based on the equation you have. You can check a few positions. Which position will give you the highest bending stress in terms of magnitude? So means negative values also you need to consider. So as shown in this example. Is it clear how to do it?
Yes, yes. And doctor, I just want to clarify something. When you go to the airport, I mean the airport. Right. Okay. Let's say this from 0 to 3 is the first section, and then from 3 to 7, where the spa web is here, is the second section.
Okay.
Okay, the first section, I already calculate the IX of the IXX of the whole section. I mean of this whole section, and this which includes this spa web from the first section. So the second section, the other 3 sides must include also the spa web from the first one, because the spa web of the first section and the second section is connected with this spa web. So does it include in the IXX calculation of this IXX of this spa web in the second section?
Why do you calculate section by section?
No, I mean the cells lah, the cells.
Why you calculate cell by cell?
That's what I did first.
Okay, to calculate the moment of inertia for the whole wing, for example, how do you calculate? You need to calculate this thing, right? Plus the contribution of moment inertia from this thing, plus the contribution of moment inertia from this thing, right? You just sum them up, everything, including also the skin. The skin we need to calculate like this one. Yeah, the skin, this line of skin contribute how much of moment of inertia. This line contribute how much. You need to sum them up, because everything, the moment of inertia, you need to calculate according to with reference to the centroid of the entire wing. So you need to use the parallel axis theorem to transfer to a new position. So eventually, the moment of inertia you get is for the entire wing with reference to the center of the wing. There's no section by section, but you need to add up all of them. Okay. For example, this angle, eventually it is a combination of these things. Okay, this one, this one, yeah, plus that one. Okay, this one, moment of inertia of this one is the moment of inertia of this one plus moment of inertia of this one, right? So the same principle applies. If you have the moment of inertia of this one, yeah, you need to sum it up with moment of inertia from this one, moment of inertia from this one, and all other components plus the skin. The skin in this diagram is curved, but you can simplify it as straight line. Okay, sum up all of them, the contribution of moment of inertia from all the components. Then you have the moment of inertia for the wing.
Okay, I get it.
Okay. Any other question? No question? No more question? Yeah, okay, so I is a t. Does it mean we calculate ixx, iyy, ixy for each line that we make and then sum all the values from that moment of inertia? How to calculate moment of inertia? I use this example. Yeah, I'll use this example to explain to you how to calculate moment of inertia. Determine the moment of inertia of the Z section shown at the right. When we want to calculate the moment of inertia for anything, for example, a beam.
Doctor tak present.
Oh, yeah. Thank you. Yeah, I'll use this example. Can you see? Yeah, when we have a beam or a wing or a fuselage, whenever we want to calculate the moment of inertia, we need to separate the parts into simpler elements. For example, this Z section we can separate into three. One, two, three. All of them are simple rectangles, right? For rectangle, we know the basic equation. That is, for rectangle, is a BD cube over 12. The basic equation for moment of inertia is BD cube over 12. If you need to calculate, to use a parallel axis theorem, because the particular beam part is far away from the centroid, then you can add plus ay squared or plus ax squared. Okay, so now the centroid of this particular Z section is over here, near here, right? Center. So for part 1, which is far away from the centroid, so we need to use parallel axis theorem for part 1. We need to also use parallel axis theorem for part 3. For part 2, because it's from top until the bottom, the centroid is exactly near the centroid of part 2. So for part 2, we just need to use the BD cube over 12 basic equation without the parallel axis theorem. Alright, so the principle behind it is, if you have a section, you divide it into different parts. Let's say 1, 2, 3 in this case. Then the ixx is simply ixx of part 1 plus ixx of part 2 plus ixx of part 3. Because 2 is unique, 2 is unique, 1 and 3 contribute the same amount of moment of inertia. So we can, in this example, we can multiply 2 for ixx1 or ixx3. They are the same. So we multiply 2. So ixx2, then we do separately, right? ixx2 is simply BD cube over 12. BD cube over 12. This one part, the first term, represent the ixx for part number 2. Then plus, sum them up, plus 2 multiply this whole thing in a square bracket. That is the ixx1, which is essentially BD cube over 12 as a basic, right? Plus area is the width multiplied height, area y squared. Okay. For ixx, you need to plus ay squared. So here, this is area, 2 brackets, area, and y squared. This is the y squared. Y squared is the displacement. Y is the displacement of the center of part 1 from centroid of the overall section. Displacement of centroid of part 1 from the centroid of the overall section. Okay, so this example shows the principle behind the calculation of Ixx. This is the same for Iyy and Ixy. So perhaps if you have a wing section like this, then you can separate, for example, this one, you can separate into this and that, right? This and that. Then you calculate, okay, you need to calculate, yeah, put it back, yeah, make it easy. You can label them, okay, 1, 2, 3, 4, and so on. Label them. So Ixx of this part plus Ixx of this part plus Ixx of this part, and so on, so on, so on. You sum them up. However, all of them, when you calculate the parallel axis theorem, you need to refer to the parallel axis. You need to refer the displacement from the centroid of the entire wing, which is given here. All right. So you refer to this centroid. When you calculate this one, moment of inertia for this one, you need to consider parallel axis theorem by referring to the displacement from this centroid. The same here, if you calculate moment of inertia for this one, you need to use the parallel axis theorem with reference to this centroid. Okay? Is it clear? Did I answer your question? You ask calculate moment inertia for each line that we make. Sum the value from that. Yeah, each line that you make. I suppose when you say each line, yeah.
Doktor, kalau saya nak present yang log file saya, boleh nak tunjuk betul tak buat?
Boleh.
Boleh? Okay, doktor, yang ini. Kita orang buat macam ni, daripada cell ni. So, kita orang cari ISS, moment of inertia daripada satu line ni, satu line ke line ini.
Yes.
Betul ke? Doktor buat macam tu? So, this one is the centroid, the X coordinate, Y coordinate for the centroid. And then for the moment of inertia, kami guna the thin wall idealization.
Yeah.
And then gunakan this formula for each line yang macam saya cakap tadi tu.
Yes.
Kami dapat untuk betul ke? And then macam mana yang saya masih keliru yang doktor cakap untuk sum up semua tu.
Okay, when you have the moment of inertia for each line, which part, line B, C, C, D, and so on, right? Then the Ixx you got is for its own or with reference to the centroid of the wing.
Centroid for each line.
Centroid of each
line, centroid, yeah.
Centroid of each line, okay. Then you need to transfer using the moment of using the parallel axis theorem to transfer to the centroid of the wing. Means
Centroid of the wing, the whole F1 shape.
Yes. Means that whatever value you have for the Ixx or Iyy or Ixy, you need to add plus ax squared or plus ay squared or plus axy.
Right.
Transfer to the centroid of the wing.
Sebab kami buat yang ISS, Iyy only for each line, tak buat untuk yang the centroid punya whole wing.
Okay, so it's quite it's just repetition. You can change your Python code. You tell the code where is the centroid, then what is the centroid of each part, then automatically it can calculate for you what.
Okay, doktor. Tapi cara kami cari ISS, Iyy ni betul kan doktor untuk line-line macam tu? Untuk each line of yang kami buat ni, betul kan? Satu line.
Saya tak pasti sebab saya belum tengok lagi equation anda.
Oh, equation semua ni guna yang thin wall tu je.
This lah, okay. A is cube. A is a thickness. No. A is a length. T is a thickness. Sine square beta. You have the slanting angle. Okay, divide by 12. Okay. Yeah, then if you follow exactly the equation is correct. This is for Ix for each line at its own centroid only.
Yeah, for its own centroid.
Yeah, correct.
Alright, okay. Thank you, Doctor.
Okay, thank you. Other question? No more question? You don't want to catch me? I think you have a lot of questions. Okay, feel free to ask. Feel free to show me your thing and then get my feedback now. You need to catch me.
I think there's a question in the chat box.
Good. I read the chat box already.
I think there's a new. Is it?
Oh, okay. If we find the centroid, thank you. Thank you, Arun. Okay, so new question. If we find the centroid according to the line, can we just sum up all the centroid to get the centroid for the F1? Sum up all the centroid to get the centroid for the F1. Okay, to answer that question, we need to go back to the principle of calculating centroid. Centroid calculation. Okay. Centroid is simply, we use this equation to calculate centroid. It's the first moment of area. It's a centroid x multiply summation of area equals to summation of centroid multiply area of each component. Okay, we can understand this equation from this diagram. If you have an area of that, if you want to calculate the centroid, you can separate it into simpler area, like for example, triangle and rectangle. Because we know the centroid position of the rectangle, we know the centroid position of the triangle. Yeah, so once we have that, we use this equation 1.2, then we can get the centroid of the entire composite area. Right, so this is the background. Let's go back to the question, how we understand this question. If we find the centroid according to the line, can we just sum up all the centroid to get a centroid for the F-void? If you sum it up and then we apply this equation, then yes, sir. If you simply sum up the centroid position coordinate, then of course you cannot get the centroid of the entire wing. So did I answer your question? You need to sum up, but you need to use this equation following this principle. You cannot simply sum up the coordinate of all the centroid of all components. You cannot sum up centroid of part 1 and centroid of part 2 to get a new centroid, right? No. You need to get the moment of area. Use the moment of area equation to get a centroid. So, is that equal? Is it okay? Okay. Yeah. Sometimes we learn a lot already, but it's quite normal for us to forget what we learned previously. So now we have a chance to revisit those those notes and knowledge we learned previously, and then it's time to use it, to apply it. Okay, you are already in the third year or maybe final year, so it's time to wrap up all the knowledge and skills you have to do something great, right? Other question? Okay. What is X bar means for the centroid? X bar is the centroid. X bar is the X coordinate for the centroid. Okay. You see, we use X bar and Y bar to represent, usually to represent the position of centroid or coordinate of centroid. As shown in this diagram, left diagram, centroid is labeled as a point with the label C. If the origin of the axis, XY axis, origin is at the bottom left corner, then the coordinate of centroid C is simply given by X bar and Y bar. Okay. So, Haika. Okay. Any other question? Is I want to ask you feedback. Can we make user interface using the Python user interface? Like when you instead of typing the actual value into, for example, field glass skin thickness, instead of typing the 2.5 mm directly in the code, is it possible to display a question for the user to type in? I think it's possible, right?
Yeah, sure, doctor.
Is it possible
Yes,
to?
that's possible.
Okay, is it possible to pop up a window, then let the key in the values inside the window? Possible? Because when we run the code, then the question will be posted inside the Python interface. Is it possible to call to display a pop-up window, and then we need to key in the values inside the pop-up window? Anyone?
Doctor, I'm not quite clear with what you mean.
Okay, when you run your code, yeah, if you ask the code to wait for input, let's say you type the question, please key in value, the thickness value. Then the code will stop there, waiting for the user to key in the value, right? Let's say 2 mm, right?
Yeah.
So instead of that, is it possible to display an additional window pop-up and let the user key in the pop-up window? Once we click enter, the pop-up window will disappear. Is it okay like that?
So you mean that we have another window to key in the information, and then the window will disappear? You mean like that? Or,
Yes.
and then the answer will be produced in the other window. Is it like that?
Yes. Is it possible to do that?
No.
I have no comment, doctor.
Anyone
Maybe
has?
can, but
No, okay.
I'm not sure.
No promises.
Maybe.
Okay. I think Ken, yeah. Any expert user here? Maybe you can answer. Okay, I think Ken, but do you prefer to modify the code every time you need to modify the calculation? Like now, okay, like for example here, we have B1 equals to 0.175. Do you prefer to key in this value inside the code? And then after that, if you need to modify anything, you straight away modify the code, the values here. But then it will be very difficult to trace back, is it? Or is it easier to do like this?
I'm not clear what you say, doctor. What do you mean? That we changing the code every time we want to get the answer? Or?
Yeah, for example, let's say we calculate the moment of inertia for this. Then after that, we need to calculate moment of inertia for this, right? And then for that, and then for that. So it means that we need to repeat the calculation of moment of inertia for many times, right? So perhaps you have a code to calculate the moment of inertia, but every time you run the code, you run it for this one, and then you run it for this one, and then you run it for this one. Every time you run the code, you need to modify for example, centroid of this part, centroid of this part, centroid of this part. Perhaps later also you need to modify or to change the value of the thickness, and so on, so on. So is that troublesome? Is that practice of changing the values inside the code quite dangerous? Which it will produce error easily. Like every time I want to run this code for this moment of inertia, I need to come to the code and change the value, and then I get the result, and then record the result. Then I need to calculate moment of inertia for this part. Then I need to go to the code and modify this value, modify that value, modify that value, and then run to get the answer. That is what I mean. Can you get it? You see, the code contains some values, right? Every time I run for different parts, I should change the value here inside the code, right? Is this convenient?
If this, for me, this is not really convenient.
Okay, so as a general discussion, how should we do it so that it is convenient to use and it will not produce an error? For example, if we forget to change this one, if we forget to change one value, we got an answer also, but we thought it's the correct answer. So how do we prevent this type of error?
Why not we ask about the shape first?
Ask about what?
I mean, like, we want to calculate, like, for example, moment of inertia, right? So for
Yes.
different shape has different formula, right?
Yeah.
So why not we ask at the first line there we ask about the shape first.
Ask about the shape.
And then we ask the user what shape they are going to use, and then for example triangle. So okay, I choose triangle, and then you key in the value, and then the answer is for the triangle only. If you want other shape, you can at the early phase you can ask about other shape. So
Yes.
you need to change every single time, right? That's my opinion. I'm not sure
Yeah.
right or wrong.
Okay. Thank you for your opinion. Just I want to ask this because like we have for a ring, we have many parts to calculate, right? So instead of changing the values every time we do calculation, and then it might create an error when we type the code. So that I'm asking whether it will be easier and safer to do like let the code constant, but we ask the code to ask we do the programming so that the code will ask for the value every time it runs instead of changing the code every time change the code.
Yes, that's much more convenient, I think.
Which one is more convenient?
The second option, we just input the
values
value,
when
yeah.
input the values when we need to do it. We need to use it. Huh?
Yeah.
Okay. All right. Thank you for your feedback. So anything else you want to ask? Any question in the question box? User input. We can create def function. What is def function? Definition function. Use input. Okay. Use input. All right. Any other question you want to ask?
I think not, Doctor.
Okay. So I thank you all for the opportunity to learn from you all. I heard the sound. What sound is that? Is that a chat? Someone raise hand? No. Not sure what's up. Okay. Never mind. I thank you all for giving me the opportunity to learn from you all. You all are doing the assignments, and I'm just talking only. I don't really understand the difficulties you all face. So perhaps from time to time you let me know more. It might help to reduce your burden. Sometimes I don't know how difficult it is to do it because I just create a problem for you and then I wait for your feedback. Okay, so it's very important that you let me know more from time to time. Okay, I think if you have no more questions, that's all for today. I'll see you tomorrow. Hopefully you do something, then tomorrow you can show me or ask me. All right?
Okay, Doctor. Thank you. Thank you, Doctor.
Thank you very much. Thank you, everyone. Yeah.
Thank you very much.
Okay, thank you.